So, in the first video, I didn't quite get the definitions right at the time, so my thinking became very confused. Interesting, isn't it? So, what we do now is to start all over on question B. So, the situation is we have a homogeneous polynomial f tilde of 3 variables, and then we have f of 2 and we have to prove that if at some point x naught point y naught at the curve that it is smooth, meaning is equivalent to the 3D gradient at that point. Non-vanishing. Now, from left to right is trivial. Because fx equals just f tilde x. So it's the other way that's interesting. That is the case f tilde z and let's just put a 1 there. Distinct from 0. Both vanishing. And couldn't we hope that that is contradicting this guy? So inserting this point x times naught plus y times naught plus 1 times f tilde z at the point equals n times naught. So this implies f equals naught. So the question was, where did I go wrong in the counterexample? Where do we use the fact that the characteristic is 0. Well, I get no idea. I can't even see where I'm using that the characteristic is 0. So we'll just have to start on C. Now, what do we have here? A tangent line at a smooth point has this equation, right? I discovered that by computing a lot of examples. Then it occurred to me, and I checked it, and it was right. But I never proved it at the time, so it's very nice to prove it now. So the tangent line. Oops, let's get a new one. It's ax minus x naught plus b y minus y naught equals 0. This does look like something. It looks exactly like x naught fx, and this of course vanishes since we are on the curve. So it equals minus zfz. Oh, that's lovely. That was nice to get that, because it's much better to compute to use this formula than using to use this formula is much more practical than this one. So I really like that I got a proof of that. That was C. D. Prove that the condition to be a smooth point does not depend upon the choice of coordinates. Why do we not? There. That is, does not change if we shift to, for example, if more than one of the coordinates are non-zeros, with no difference if we choose to regard that. Yeah, of course. So that means that we must differentiate, not implicitly, or using composition of functions. Now, my idea in this is that this A will just be multiplied by ABC here. So it's a linear combination of them. And since A is invertible, we cannot get into the naught vector if they are not naught themselves. So we'll just have to check those details. Do we need to do that really? Nah, it's simply an application of the chain rule. Now to E. Prove that the condition that a given L be tangent to C at a smooth point does not depend upon the choice of coordinates. I would actually like to prove this by showing that the line comes as a linear approximation to the curve. But then, of course, couldn't that be different with different coordinates? So it's about the transformation of, what I should say, of this equation. And now they say choice of coordinates. Then will they only take a linear transformation, or should we work with any transformation? Of course, we can only take a linear transformation, because if we change to curved coordinates, then the tangent would not be a straight line anymore necessarily. So it's only a linear guy. So this is the same again. I guess we have to go through the details. Oh, this is annoying. This is easy to do on paper, and it's a little difficult to do here while recording. So we define x tilde, y tilde, z tilde by x, y, z, a. And then we have a new function, g tilde, equals f tilde of x point, y point. We should, instead of writing it as function, write it the modern way. So on this point, a works, and then f tilde works. Just put points to say that they're working on it. Now the point is that we do have the same curve with just different coordinates, so it's the same tangent. So we have to show that the tangent line is transferred correctly. So we need to have the differentials here. And differentiating with respect to a tilde, that's another thing. Now it seems a little wrong here. This, we have to put a to minus first over here. So now we can differentiate with respect to, so it's df, what is that called, the matrix here, df dxi. That is the gradient of f. And we operate on it with the inverse of a. And now the equation is dot the gradient of f equals naught. Maybe we should change the sequence there. Where the gradient is evaluated at the point x naught, y naught, z naught. And then we can just insert a inverse and a. And this is grad g with respect to the tildes. The tilde coordinates times x tilde point y tilde point y z. So it was just the chain rule. Yeah. So the only thing we need is to give a counterexample if the characteristic of K is non-zero. Wow, wow, wow. I remember an exercise in section 1 where I had problems handling fields of characteristic non-zero, and I must admit I don't feel quite comfortable with them. So I have been doing a few examples with such fields, but not enough to feel really comfortable with them. So I'll take another cup of coffee and see if I get it. Oh, I don't have any more time today. So I'll just stop here and then hope I get some idea and then record it tomorrow. Bye bye.